Hello, I am Alvaro Chavarria, and I will be presenting on the Selena neutrino experiment. I will start first with the Selena detector concept, then I will report on our R&D progress and status, followed by the prospects for neutrinoless double beta decay. I will also comment on prospects for a zero background solar neutrino experiment with Selena, and then I will talk a bit about what physics you could do with the results from solar neutrino spectroscopy. So here is the Selena detector concept. It was proposed in JINS in 2017. The idea is that you have amorphous selenium deposited on large area CMOS pixel arrays. And you have a high voltage contact here, so you can apply an electric field across the amorphous selenium and collect the charge on the pixel array. This allows you to image with high resolution particle tracks. So selenium-82 is a double beta decay isotope. So in principle, you could image a double beta decay event, something like this, where you have a vertex, you have these very, very nice tracks, and you have the Bragg peaks that tell you there are 2 electrons. A detector like this would be built with many, many modules on a tower like this, so you can fully contain the event. One thing that is very important for Selena, especially in terms of background rejection, are the spatial coincidences. So this is inspired by data from DAMIC, which is the experiment to which I'm the spokesperson, which is another imaging solid state detector. So here you can see in DAMIC, which uses highly pixelated CCDs, a lead to 10 decay that is followed by a bismuth to 10 beta decay and then polonium to 10 alpha decay. And even though these events happens with days of separation, you can identify them with very high efficiency because they occur exactly in the same pixel over millions of them. In DAMIC, this has been incredibly useful to mitigate one of our bigger backgrounds, which is silicon-32. And you can see here silicon-32 decaying to phosphorus-32, which is a 14 days half-life, and we can tag and reject these decays. And this was recently reported in JINS, where you can learn more about this strategy, which we will exploit actually quite a bit in Selena, you'll see. So the detector goals of Selena is to have an experiment with an excellent energy resolution so we can perform precision spectroscopy. In the case of neutrino double beta decay, this is crucial for distinguishing the 0 neutrino signal from the 2 neutrino signal. We want excellent spatial resolution because the backgrounds are suppressed by event topology. In the case of rejecting, say, single electron backgrounds from the neutrinoless double beta decay search, we need to count the number of Bragg peaks, but also, the decay sequences are what let us reject most of other types of radiogenic backgrounds. We want something that is easy to build. This detector would run at room temperature or very close to room temperature. The radiopurity requirements are not stupid and stringent because of the capability of reject backgrounds by particle ID and spatial coincidences. And also, it will be fully active and fiducial to target. So there's no need to fiducialize. So it's a bit of a different concept than other types of detectors. But it makes it not having to fiducialize allows you to get away with a smaller total mass of your detector. And then we want it to be scalable. And so we're focusing on CMOS pixel arrays that can be done on a standard foundry process on 300mm diameter wafers, so you can make them big, and use an industrial amorphous deposition procedure that has been developed in the medical field. So here we are, 2021, we have a small prototypes. 2024, we'll have a large detector module, hopefully about 1/4 kilogram, which will be the building block for building 100 kilogram demonstrated by the end of the decade. And then the goal is to have, in the following decade, the construction of a 10-ton detector underground that can do physics. And I will be talking about the prospects of this large detector. So let's talk about the R&D, which was recently reported in JINS again and this year, where we actually started learning how to use amorphous selenium by making a very simple, what we call a single pixel detector, where you have a sandwich of amorphous selenium between 2 electrodes. And then we illuminate it with a cobalt-57 source, where you have photoabsorption in the amorphous selenium, and then the photoelectron deposits energy, and then you can drift it and collect the charge. And then you connect this basically to a digitizer, and we had very, very nice response, and we could see the pulses. And the shape of the pulse is actually related to the depth of the interaction. So we are actually measuring not only the charge yield in amorphous selenium, but also its charge transfer properties, which are crucial to build a good detector. And here you can see basically our measurement of the resolution of function of energy, which we can extrapolate down to the double beta decay Q value of about 3 MeV, and this gives you basically our expected resolution, which we'll use to see the prospects of this experiment. We've also moved on to R&D on the actual pixelated chip. So this is based on the Topmetal-II chip from Yuan Mei in Berkeley lab. You can find details about this chip on a NIM paper here. So we basically start with this chip. We have exposed bare metallic contacts. We deposit amorphous selenium on it. Then we put it on a test board, we connect it, we bias it, and bam, you can see here, we can see electron tracks as we turned this guy on a few months ago. And this is the first demonstration of imaging single events in amorphous selenium. We are currently characterizing it further, but so far the results are very encouraging. I will note that the pixel size of top metal is 83 micrometers squared, and the pixel noise is quite good. It's about 15 electron noise per pixel. So where are we now? So we measured the energy response of amorphous selenium. We coupled the amorphous selenium chip to a CMOS pixel array. We are already characterizing the response of our first imaging sensors with radioactive sources, and you should expect a publication in the coming months. So what I will do now is present the prospects for a neutrinoless double beta decay search and solar neutrino spectroscopy, assuming an experimentally informed detector performance in an exposure of 100 ton-years. Now, I will mention there's too many opportunities to improve the detector performance beyond using the standard top metal specifications. I will mention when those might be needed. But we know we could improve the energy and spatial resolution by having a thinner dead layer, smarter energy reconstruction, smaller pixel size, and so forth. So here are the prospects for the neutrinoless double beta decay. So the first thing is that background suppression we've studied with simulation. So one of the key properties of Selena is that this is basically with 5 by 5 micrometers per pixels. If you can image these tracks, you can see the difference between a single electron event, which starts pretty straight and then has a single Bragg peak, from a double electron event, which has 2 Bragg peaks from the 2 electrons. This gives you about a 1 in 1,000 suppression of single electron background with 50% signal acceptance. And those details are in this publication. And then there is also bulk background that can be suppressed by alpha, beta particle identification, spatial correlations, and so forth. And the bottom line is that we think we can achieve a background rate of less than 6 times 10 to the 6 times 10 to the minus 5 per keV per ton per year. This may allow you to do with 100 ton-years search for neutrino double beta decay that can put an a lower limit on the half-life of 10 to the 28 years. As I mentioned, the pixel size here is 15 by 15 micrometers squared. That's what you would need to this performance, and then you would need to decrease the dead layers of the detector to 10 micrometer. But the energy resolution here in this projection is basically what we've measured in the lab. So this is actually not already demonstrated. Could get better if we were to improve the energy reconstruction by using information on the tracks. In particular, the energy reconstruction resolution is dominated by dependence on the charge yield on the electron track energy density. So if that could be corrected for, this could get better. So on to solar neutrinos. Solar neutrinos have been identified as a background for searches of neutrinos double beta decay in selenium-82. This is a paper from Ajiri and Elliott that pointed that out. Now, this is not a problem for our neutrinos double beta decay search because the captured product, bromine-82, is a beta emitter, which allows you to use a decay sequence that can tag it and discard it. So here is a decay sequence. You have a neutrino that is captured by selenium-82. Then you get bromine-82 in an excited state. And then you get an electron, which carries information on neutrino energy with a relatively low threshold, 122 keV. Then bromine-82 decays to its ground state, and there's another emission there with a half-life of 6 minutes. And then bromine-82 ground state itself is radioactive and then decays with a half-life of 35 hours to krypton-82 with another number of electromagnetic energies, betas and gammas. So you have what we call the triple coincidence. Here is just the schematic of the energy levels. And just as we can use this to tag events with high efficiency for reject them from the neutrino double beta decay search, we can actually tag them and use them for solar neutrino spectroscopy, because by looking at the prompt, we get the energy of the neutrino. So let's talk about backgrounds when you were to do this for solar neutrino searches. So the number of expected accidental events in 100 micrometers per pixel, for example, which is bigger than a top metal pixel, but perfectly doable, so which is only about 22 micrograms of amorphous selenium, is that's a 10 to the minus 4 in 100 ton year. So basically, they're, forget about accidental background, they don't matter. Even assuming, this is the background we would be assuming, which is quite modest expectations for a solid state detector underground. Then there are other backgrounds you have to care about, of course, because you could produce, say, bromine-82 from PN reactions or something like this. But all of these ways to produce the excited state of bromine-82 have a very different prompt event. So they can be very effectively rejected by event topology. Then we did a survey of cosmogenic isotopes that could be produced in selenium-82 to see if there could be something that mimics a triple coincidence, and there really is nothing. Some neutron captured selenium isotopes can give triple coincidence, but again, their event topologies are also very different. So it seems right now that there is no identified background that can mimic this very, very special triple coincidence. And so I think there's a very strong possibility that we could do zero background neutrino spectroscopy with Selena. So let's talk about what you could do with these solar neutrino measurements. So here are the brief introduction of solar neutrinos. They're produced by nuclear reaction in the sun. You have here the PP and CNO cycles, PP in black, CNO in blue. And these are their flux are basically predicted by solar models. Then as they travel to Earth, neutrinos undergo oscillations, and then you have what's so-called the survival probability, which is the probability of the electron neutrino to remain an electron neutrino. And at low energies, you have what is called a vacuum-dominated region, here where matter affects matter, and then you have this so-called transition region. And all of this is predicted by just standard neutrino mixing matrix parameters. So what does the prompt spectrum would look like? So again, neutrino captures selenium-82. We get the capture cross-section from this paper. Then you have this excited bromine-82 nucleus that you tag, and then you have this electron that contains the energy of the neutrino. And if you look what you expect on a Selena type detector, you have the PP, CNO, beryllium-7 PP. Again, these resolutions are based on our understanding of our measured properties of amorphous selenium. And then these are the number of events you expect 100 ton years. And here you have basically just the statistical uncertainty from a counting experiment on the different neutrino species. So what could you do with these results? So in terms of solar physics, you can measure the solar luminosity quite well. Now, the statistical uncertainty in the rate will be about an order of magnitude lower than Borg-Seen. We're talking about 1%. But then if you want to translate this to a flux measurement, then your uncertainty will be dominated by the nu-e capture cross-section. So one thing you could do very simply, just calibrate it to nu-e scattering in Borg-Seen by comparing the beryllium-7 rate in both experiments, and that gives you a systematic uncertainty about 3.5%. Maybe if you could measure this cross-section in the lab, you could do much better than this. Then you could measure solar metallicity. So the CNO flux would be measured to 13%. The difference between the high and low metallicity solar model predictions, their central value is about 28%. So I think this is likely could constrain significantly that problem. And the last thing that is nice that you can do when you're measuring the neutrino energy is measure the solar core temperature. This is a paper from John Bacall from 1994, where he says beryllium-7 line position would be different from the sun than what you would measure in a laboratory on Earth. And this difference you could measure quite well, and it tells you something about the temperature of the sun. And you can measure it. You can measure this line difference to 26%. And for PP, these are numbers that I got from Carlos Peña. You can measure it also to 21%. And these two will tell you about the distribution of basically the core temperature of the sun, assuming two different distributions of neutrino production. So it's quite exciting. And then for neutrino physics, you could measure the PP to PP rate ratio to 8%. So this flux ratio is very well predicted by a standard solar model. And the MSW effect should suppress the PP flux by 7%. So even though you won't be able to really measure this difference to demonstrate the onset of matter effects, if you have non-standard interactions, which were to increase the matter effects at the PP energy, you would be able to measure it. So basically, this would constrain significantly non-standard interactions. So it's a sensitive probe also for neutrino transport in the sun. So here is my conclusion. A large Selena detector has the potential for background free search for neutrinoless double beta decay and solar neutrino spectroscopy. We could place a limit on the half-life being greater than 10 to 28 years on selenium-82. This corresponds to about Majorana neutrino mass smaller than 10 milli-electron volts. We can measure basic properties of the sun to validate our solar models and stellar models. Our R&D program is going great. We already fabricated and operated the lowest noise single pixels amorphous selenium sensor ever. We demonstrated the amorphous selenium can be coupled to a CMOS pixel array, and we've already imaged electron tracks. And our R&D program continues to characterize and optimize the CMOS amorphous selenium sensor toward a larger module to be the building block for Selena. So thank you very much for your attention. Here are the list of collaborators from the University of Washington, Berkeley Lab, and Princeton. Have a good day.